Hurricanes rank amongst the most dangerous storms on Earth. They inflict losses of billions of dollars each year. Only the forecast helps save society from the worst of their impacts. Yet despite constant international scientific effort, we still don't understand their most dangerous shifts of mood. For a hurricane can explode to extreme and lethal strength in just a few hours, and nobody fully understands why. Each year, the tropics undergo trial from the most powerful storms on the planet. Worldwide, they go by different names. Typhoon in the Pacific, cyclone in Australia, and in the tropical Atlantic, hurricanes. All are names for storms born from almost identical circumstances. All have the unique visual signature of a disc-like storm system, rotating around a calm eye of extremely low atmospheric pressures, with winds accelerating ever more viciously towards that center. All are potentially deadly. Minimizing their impact is a task that lies at the heart of hurricane research at NASA in the United States.
We need to understand how hurricanes form and how they intensify so we can predict them. So we need basic conceptual understanding so we can make practical forecasting tools. No one is going to forget that in 2005, Hurricane Katrina hit the United States and killed almost 2,000 people. But this is a worldwide problem. We should all care about this.
The cost of major storm landfalls can be staggering. In Honduras in 1998, Hurricane Mitch made 1.5 million people homeless. More recently in the USA, Hurricane Sandy had an economic cost of over $68 billion. The University of Miami is directly in the hurricane firing line. Scientists here are acutely aware of the need to improve the forecast.
Hurricanes are part of nature. They occur. Some are not so severe, some are very severe. For us, it's an important geophysical phenomena that occurs in nature. We would like to understand them more, and by improving the understanding, we improve the models.
The models are simply numerical representations of nature that attempt to predict the weather and are core to Joe Sione's research at NOAA's Hurricane Research Division.
How do these models work? Well, it's code, it's math, it's physics. The physics that's used in these models, though, make a lot of assumptions called parameterizations. A lot of parameterizations in there were developed decades ago. Guesses, if you will. Good guesses maybe in some cases, but guesses nonetheless. The end game is improving our ability to predict this phenomenon.
The very first of those guesses in hurricane prediction was made in Cuba. Jose Rubiera, director of the Institute of Technology Cuban Weather Service, is the latest in a line of forecasters that began in 1875 with Padre Viñez.
He was a big figure, a member of the Cuban Academy of Sciences, a forecaster of hurricane. He was the first ever in the world who issued a hurricane warning on September 1875 in Havana, Cuba. It has been authenticated as the first hurricane warning in the world. So when he died in 1893, he had written 2 books about hurricanes, and one of them was a complete theory about the structure of the hurricane and how to forecast a hurricane with the means they had at that time. But they didn't have satellite nor anything more.
With almost no meteorological data, there was little improvement in the forecast prior to the formation of the National Hurricane Center in Miami in 1956. Even then, there was almost no way of observing hurricane formation over the ocean. But all that was set to change.
Some of NASA's first launches were weather satellites in the 1960s, including a satellite that had an infrared camera. That infrared camera let us see the world in a new way. Never again would hurricanes take us by surprise. And ever since then, we've been launching satellites with infrared cameras. There's a fleet of them circling the Earth in geosynchronous orbit.
There are as many as 3,000 in orbit. Among them, the workforce of weather satellites, part of the high-tech scientific effort to research and improve the hurricane forecast. Better prediction of storm direction of travel has resulted from radical refinements in observing systems, tools that sharpen the forecasts at the National Hurricane Center in Miami.
The accuracy of the National Hurricane Center track forecast has improved greatly over the past 20 to 25 years. So much so that we've actually cut our forecast errors by more than in half over that time period.
But what they don't do a good job at is that rapid intensification. The computer models are not yet consistently and accurately forecasting rapid intensification or rapid weakening, and the forecasters can't do that either. So we've got a long way to go there.
Rapid intensity changes are still capable of catching forecasters by surprise, risking serious consequences during hurricane landfall. With populations in the Caribbean and coastal U.S. expanding at well over 300 million people, the need to predict the storms more accurately is ever more pressing.
With the increase in population, it takes more time for these people to evacuate and move out ahead of a storm. So it requires better and better hurricane forecasts to try to refine these hurricane warning areas and also the areas in which people need to evacuate from.
Hurricane Sandy is remembered for its massive impact on the northeast U.S. coast. But earlier in its path, this was a storm that underwent rapid intensification prior to landfall in Cuba.
Sandy was not a surprise. We made a good forecast. Sandy went from a Category 1 hurricane to a Category 3 hurricane only 17 hours. So it was a very fast increase in intensity.
When it passed over Cuba, Sandy was a major Category 3 hurricane. But at landfall in the USA, it had weakened to a Category 1 or less. Even then, its size and the effects of the storm surge wave heights caught many by surprise.
This is the back of our safari ride. As you can see, the water came out from underneath the boardwalk and took up all the piling, all the boardwalk, the ramps, and did some pretty good damage into this ride and the pier that's connected to it.
10 to 15 seconds, it'd be gone. It was like going about 50 miles an hour heading south. Something I'd never seen before, and then I realized that there was some real destruction going on because I'm seeing almost Whole sides of houses going past my house in the ocean.
What I saw was 3 foot of ocean water coming down both sides of the street. After looking at the waves for 10 minutes, I realized that all the oceanfront homes were going to get punched out.
You know, there wasn't very much rain. The rain was very light, but the wind was absolutely incredible. You know, I've never, ever, even with all the other hurricanes that have, you know, come through, Irene, et cetera, I'd never seen the ocean quite like that.
Sandy left an indelible imprint on the consciousness of the USA. But although huge in size, it was barely a hurricane when it struck land. It is the probability of a similar-sized storm undergoing rapid intensification prior to landfall that haunts forecasters.
Kind of one of our nightmare scenarios is to have a storm rapidly strengthen as it's nearing land because it can increase the amount of surge, storm surge, the amount of impacts from wind, the stronger the storm get.
Bursts of rapid intensification are common in many of the most famous storms, like Camille in 1969, Katrina in 2005, and perhaps most famous of all, Hurricane Andrew in 1992, which leapt from a tropical storm on August 22nd to a Category 5 hurricane at landfall just over a day later.
Loosely speaking, though, rapid intensification could be 20 knots in 12 hours or something like that. In fact, some of the most famous storms that rapidly intensified, like Hurricane Andrew in 1992, intensified huge, 45 knots in just 12 hours. That's rapid intensification for sure.
With little advanced warning, Hurricane Andrew crashed into South Florida and left the unprepared city of Homestead utterly demolished in its wake. The scenario that NOAA's hurricane hunters try to ensure never happens again.
If you told someone it was going to be a Category 1, maybe they would decide that it was okay to stay on the beach and not have to pull the boats out, etc. And if it shows up as a Category 3 or Category 4, literally the storm surge could overwhelm the populace and destroy the boats, the houses, etc. And it could be quite devastating to those people and for the forecasters themselves. No one would believe you the next year.
Each and every day as a forecaster, we come in and we assess what our needs are for flying aircraft for the next couple of days. If there's an area of disturbed weather that might form into a tropical depression or tropical storm, we will task aircraft to go out and investigate that area of disturbed weather.
The only way to get data where on our terms, meaning that we want to collect it, is to go there. For decades, we've flown into the eye of the hurricane.
Most of the time, the path that we take to the storm is the direct path. This plane is fast enough, strong enough, and can take pretty much anything, so that we want to be as precise as possible. We cut a straight path. We only deviate if we absolutely have to, and we do on occasion. Well, the principal role of air ops, or actually flying in the storm and the hurricane, is to actually get what they say is in situ measurements, or measurements in the storm itself. Then we can report back to the National Hurricane Center what's actually occurring in real time in the storm itself, because satellites just can't see down through the clouds and the rain. You actually have to send an actual person in, and we do it here in this vehicle called a P-3 Orion. Well, the real-life experience of rapid intensification is that you brief, and during pre-flight, you'll spend 2 or 3 hours preparing the plane and briefing with the scientists. You'll expect one level of storm, and usually it's lower, and then you get to the storm and you have something that's quite a bit different, quite a bit stronger, and usually growing. You know, one of the worst scenarios you can be in is a tropical storm trying to be a hurricane, which can be quite painful.
The hurricane hunters ride the hurricane for as long as their fuel load safely allows them. The data they obtain helping to form a picture of the storm's state of health. What exactly makes a healthy hurricane? The first ingredient is tropical heat over an ocean. So hurricanes are beasts of the tropical Atlantic, Caribbean Sea, and the Gulf of Mexico. Many of the storms have their origins from weather disturbances coming off the coast of Africa, called African easterly waves.
Now, most of these systems that come off Africa do not become hurricanes. I would say somewhere on the order of 9 out of 10 do not. So you have to have a lot of things right for it to occur.
Between May and November, these African easterly waves progress west across the Atlantic every few days. The next ingredient is a warm ocean, with sea temperatures of 79.6 degrees Fahrenheit as the usual trigger point. Air in the form of wind blows across the oceans from regions of high atmospheric pressure to low. As the tropical disturbance travels across the ocean, the winds evaporate heat and moisture from the seawater. The warm, moist air forms more and more thunderstorms, with the air inside them rising upwards by as much as 60,000 feet.
So as you get this warming, you get pressures that reduce. And as the pressures start to reduce, you start to get the winds start to accelerate towards this incipient disturbance.
The winds rush faster and faster towards that low pressure and the growing thunderstorms, which pump hot air into the stratosphere. When that low-pressure storm core becomes sufficiently developed, the weather system starts to be influenced by planetary forces. The storm is now ready to grow through the different stages, to metamorphose into a hurricane. To measure the strength of the growing storms, the forecasters categorize them by wind speed. As a Category 1, it will only have sustained winds of between 74 and 95 miles per hour. As a Category 5, it would need winds of over 157 miles per hour. With the strongest recorded hurricane having winds sustained at over 190 miles per hour. The storm's fate will be determined to a large extent by atmospheric winds surrounding the system. If they are at different speeds or directions at different heights, they will prevent the storm from growing.
What happens? The storm tends to tilt over. Think of it getting decapitated. It doesn't like that. It wants to remain vertical.
This difference between wind strengths at height is called shear. If the difference is large, the shear is high and will cut the storm to pieces. If the shear is low, the storm can grow. Once in range of the P3 Orions, the NOAA hurricane hunters fly research patterns back and forth through the storm. Measuring atmospheric conditions within a hurricane is vital to determine if wind shear is suitable for intensification. For that, they need to put instruments into the storm itself.
So we developed this technology, this drop-son technology. It has sensors here for pressure, temperature, winds, and humidity. And as it drops from the plane, falls down, and within 2 to 3, depending on the altitude we fly, hits the water.
But in those few brief minutes, the sons record vital, precise observations from the very worst conditions in the weather systems below. During the flight, they drop many hundreds of sons into the hurricane. As they fall, each of them transmits weather data back to the aircraft.
Think of it as a picture, a snapshot. It gives us a profile, but where the winds take it tell you where that profile is. So it's not even a vertical profile.
The data profiles help to locate the eye, the very center of the storm, where weather conditions are completely benign.
When they say hurricane hunter, what you're doing is you're hunting the eye by keeping the wind at your 90 degrees. So as the wind changes, you change the nose of the aircraft until you find the exact center of pressure, low pressure, and the lowest winds, which theoretically are 0.
This is also where the most vital core of the growing hurricane is found, the eye wall, the narrow band of intensely convective thunderstorms that encircle the central low-pressure eye.
The part of a hurricane that energetically is, I would say, the most important is the eye wall. So just beyond that clear eye, there's a ring, or at least an arc, of strong storms. And it's there in the eye wall that all of the mass that's circling in at the surface and then spiraling out at the top, it has to pass up through the eye wall. In fact, it's just sometimes updrafts half a kilometer across.
The system is by now a weather heat engine. Warm air, in the form of increasing winds, spiral towards the eye, where they encounter the convective thunderstorms of the eye wall. The winds are swept high towards the stratosphere, where they radiate outwards for thousands of miles.
I think of a hurricane as a marathon runner, and I think of thunderstorms as sprinters. They're fast, but then they have to stop. So a hurricane can keep going for weeks, as long as it doesn't hit land and lose its oceanic energy source.
But a hurricane is an unpredictable beast that can change intensity in a matter of hours at any time. To try and predict those changes, research scientists build complex computer programs. When observed weather data is put into these mathematical models, they can calculate future weather trends. But it is far from simple. NOAA's Hurricane Research Division tests models in development to ensure their value for improved forecasting.
One of the techniques that we're using here at the Hurricane Research Division to improve the accuracy of the models is to increase the resolution of the model.
Our track forecasts have improved greatly during that time, while our intensity forecasts have not improved as much. And it's because in track forecasting, the tracks of storms are more governed by these large-scale features in the atmosphere. These very large high-pressure areas or low-pressure areas help to steer the storms, and that is fairly easy to model.
Increasing resolution has allowed modeling of hurricanes in sufficient detail to predict the atmospheric steering of their tracks.
As these computer models have gotten better and better, they've been able to see these large-scale features and know how they're going to move over the course of the forecast period and how they're going to evolve and where the storm may go.
The resolution hurricane model impacts how we are able to resolve processes happening inside the hurricane.
Ultimately, the credibility of the forecast depends on being able to predict rapid changes in strength. The question is how? Why is it that improving field observations and computer models are working better for track forecast, but still fail fundamentally with rapid intensity? So the first step to understanding what processes drive rapid intensification is to improve the fine detail of weather data. And for that, you need to get down and dirty. Scientists realize that the best approach is to venture into the storm's heart, equipped with high-tech specialized instrumentation. The University of Florida's Hurricane Research Team is led by Forrest Masters.
So for many of you, this will be your first time traveling into a hurricane. I need you to listen closely. We're going to push hard to intercept the storm. It's absolutely imperative that you follow my instructions, stay vigilant, and let me know if there's anything that's going to prevent us from collecting data or creates an unsafe situation. So weather deteriorations, they're going to deteriorate quickly. Just stay alert. Let's get to work. Deploying on such short notice creates a lot of logistical issues. We have to think about fuel, where we're going to set up, where we're going to lodge, what's our evacuation strategy. We have to make all these decisions on the fly. Generally, as we're driving into the storm, most of these decisions get made. Once we leave, we drive directly into the storm. Using aerial imagery and local knowledge of the area, we deploy the equipment and sites that are expected to be in the worst winds.
As Hurricane Isaac threatened a first landfall over the Florida Keys, Forrest and his team raced to get the instrumentation in the path of the eye.
Data are scarce in tropical cyclones worldwide. If we look specifically at the United States, there have been significant historical moments where we've had a major event and we've had very little data to rely upon post-event. So even today, when a storm happens, it's very unlikely that we'll have intact wind speed records from the fixed weather stations that are out there. So we have this specialized mesonet, which is essentially a collection of weather stations that we deploy in the path of the landfalling hurricane. And this gives us the high fidelity information we need to reconstruct what happens at landfall. We work using portable instrumented towers that have specialized instruments that characterize the speed of the wind and also the diameter of the rain particles. The importance of this technology is it allows us to reconstruct the rain intensity, which we can compare directly to the wind speed at that particular site. And so for the first time, we're able to look at how do the winds and rain evolve as rain bands and other features move through the impacted area.
The storm barely brushed the Keys before heading across the Gulf towards Louisiana. With over 1,000 miles to drive, Forrest's team were up against the clock to catch up.
We have very few chances to conduct these experiments. We have to seek out the most heavily impacted areas, which always brings us in the vicinity of the eye wall. We're looking for the radius to maximum winds, and that's the distance from the center fix where we expect the most severe winds to happen. Hurricane Isaac is a very unusual storm. It intensified right before landfall. Now it's moving through, and at the speed that it's moving, it's going to take some time before it leaves the area. Isaac presents a fantastic opportunity for the research community. There are literally dozens of assets spread across the state right now collecting data. Many of these are co-located, so we'll be able to go back, look at what's going on aloft, and be able to compare to what's going on below. This is a real first for our field.
Teams of scientists gathered precise high-resolution wind, rain, and Doppler radar data directly under the eye of Isaac. Analysis of such events will give greater understanding of the small-scale features that create the structure of the hurricane's eye.
These data are used by many disciplines outside of engineering, including meteorology, hydrology, and other fields. For example, the type of wind-driven rain data we're collecting can be compared directly against the predictive models that are used to predict the rainfall deposition in an area using radar information. Ultimately, we are strengthening the knowledge base by going out and collecting information that really simply doesn't exist. And over time, through more and more storms, we'll build a large database that we can turn back to hopefully develop better predictive models.
Even with more intimate data sets, opinion still varies as to what exactly drives intensity change. Nick Shea of the University of Miami explores the impact of ocean water temperatures. He sees a strong connection between sources of warm water and intensification.
The detailed focus of our research with hurricanes is trying to assess what is the role of the ocean in rapid hurricane intensity change.
Sea surface temperatures are a measurement of the outer skin of the ocean and no indication of water temperature at depth. So Nick and his team map deep warm water areas that extend many hundreds of feet below the surface. Called warm pools, sumps of water hotter than 78 degrees Fahrenheit and up to 200 miles in diameter. They are vast reservoirs of heat energy for passing hurricanes. In the northern Caribbean, numerous deep warm pools calve off from the currents of the Gulf of Mexico Loop and the Gulf Stream. NOAA flies Nick and his team to research any hurricanes heading for a warm pool. They drop special submersible sondes that transmit precise data from hundreds of feet underwater. Information that shows what happens when a hurricane crosses a warm pool. The result is chilling.
And then subsequent to Andrew, there was a major hurricane in the Gulf of Mexico that directly went over a deep warm pool, and the name of that storm or hurricane was Opal. Opal went from a Category 1 to a Category 4 storm in 14 hours, rapidly intensified, and became a very strong storm in the Gulf of Mexico, right over one of these deep warm pools.
The storm spelled disaster for the people threatened by landfall in the northern Gulf of Mexico. Only the fact that Opal weakened on crossing colder water saved them. Nick and his colleagues are convinced it is vital to know exactly where the warm pool features are when a hurricane threatens landfall. October in San Juan, Puerto Rico. Oceanographers are not alone in their interest for warm pool distribution in the ocean. Sport fishers preparing for the annual San Juan International Fishing Contest. In search for ever-improved data to pick out where warm pools are, Nick Shea has begun a new collaboration to take advantage of a most unlikely ally.
It turns out that my colleagues here at the University of Miami like to tag fish species like blue marlin.
The satellite tag technology helps them find out more about oceanic fish behavior.
One of the areas of fertile research that are currently going on here at the Rosenstiel School, where we're actually tagging fish with temperature sensors, and as they go down looking for food and come back to the surface, they actually send temperature profile data back to the satellite that we can pull in to help us look at these, look at the temperatures. And the beauty of the fish is that they can actually swim against the current, where we actually need the data the most, because that's where the deep warm pools are.
Marlin seek the 79-degree temperature gradient around warm pools for very good reason.
The blue marlin love to be in the vicinity of these deep warm pools. Along these deep warm pools are areas of upwelling. In other words, cooler water is coming to the surface. These are smaller scale ocean features where there's a lot of food for these marlin and these sport fishes to feed upon.
The object of the game is to catch sport fish and attach satellite tags before release. The tags record information that may be invaluable for the ongoing search into the causes of rapid intensification.
We have a case where we had Hurricane Ivan. There was a tagged blue marlin on July 3rd, 2004. So this was before Katrina. It turns out that this one blue marlin was just lingering around this big warm core eddy right on the perimeter where the cooler water was. And what happened was during the period that he was in the northern Gulf, Hurricane Ivan came into the Gulf of Mexico in mid-September. So as Hurricane Ivan moved towards the north, This blue marlin went actually underneath the track, and we actually have a couple of profiles characterizing the upwelling or the cool temperatures that the fish saw where all this upwelling was occurring. And when I say upwelling, it just means colder water is coming towards the surface. It's very clear the ocean is playing a role in intensification. Now, you might want to argue how much.
Now forecasters do take ocean temperatures into account for predictions, but many researchers believe the causes of intensity change lie elsewhere.
The specific area that I'm very interested in is looking at how the enormous amount of energy that's stored in the ocean when we think about hurricanes, how does that energy get to the atmosphere? I think the air-sea interface in a hurricane, particularly in the high wind region, is critical. So if this is our ocean, this is our atmosphere, we're talking about an area that's very close to the surface of the ocean and, say, 30 feet or 10 meters above the ocean. This is the area we're talking about. This is the traditional way we calculate flux. That is, how much energy, either heat energy or, even more important for a hurricane, moisture energy gets out. So that is determined by the thermodynamics of that gradient.
Heat energy moving from the water is governed by the humidity of the air above it. And Joe believes that if the saturated air at the center of the hurricane's eye gets slightly drier, it will be able to absorb more water and heat from the ocean.
So if you can have a change in relative humidity, which looks pretty benign, 95%, 90, still pretty humid, right? That type of difference in high wind conditions can be a tremendous boon to the storm as far as intensity change goes. You could be looking at energy 30, 40, 50% more drawn out of the ocean than otherwise would have been the case. And if you have that situation over several hours, you don't need a lot of time. If you're looking at 5 to 6 to 10 hours, that can be the difference between a Category 1 and a Category 3 or Category 4.
The wave tank at the University of Miami helps Joe observe the saturated conditions that wind and waves create immediately above the ocean surface. He believes a very small drop in humidity from downdrafts will fundamentally affect the energy flow.
That will change that gradient, that vertical gradient, and allow more moisture, more evaporation to get out of the ocean, just enough to really make a difference in the storm structure. By changing how much energy comes out, we also can change the actual intensity or the wind speed of the storm. So that change in energy, if you're changing the energy by 30% or 40%, you're essentially allowing the system to jump from, let's say, a minimal hurricane, 75 miles an hour or so, to a major hurricane well over 100 miles an hour in a very short amount of time.
Proof of the theories for rapid intensification require better data. At Wallops Air Base in Virginia, scientists from NASA prepare a revolutionary observational platform to provide just that, the Global Hawk.
The Global Hawk is really an incredible airplane. It's a combination of both an airplane and a satellite. It flies at about between 60 and 65,000 feet. That's about twice as high as a commercial airliner. It can fly over 10,000 miles, or it's about 12,000 miles actually.
Of key interest is obtaining observations of a storm over enough time to be able to capture the processes that drive rapid intensity changes. With a flight time of over 36 hours, the Global Hawk is a big step forward towards doing that. The entire research and flight team are ground-based. Scientists will monitor data coming from the aircraft in real time throughout its mission. The pilots prepare the Global Hawk for a flight across the Atlantic Ocean and back. Yet it will still conduct nearly 24 hours of research time over the storm.
One Global Hawk is equipped with instruments to look at the the near field around the storm, so we can look at how winds around the storm are controlling storm motion and how they might be impacting the intensification of these storms, how they change from a tropical storm to a Category 1 hurricane. The other platform has a series of instruments that can look directly through the clouds into the guts of the storm. The Global Hawk can take off from the coastline in the U.S., fly all the way to Africa, sit on top of one of these forming hurricanes for 10 hours, and then fly all the way back. Manned aircraft are simply not capable of flying that long and that far.
7 a.m. next morning, Global Hawk touches down after its mission to Africa and back. With rapid intensification still an unsolved mystery, perhaps there is one more perspective that may yet prove to be the most conclusive. Eyes from space. Scientists from NASA Goddard have been looking deep inside the hurricane clouds with a special satellite and radar. In 1997, the TRIM satellite was launched, and it has been relaying revealing data to Earth ever since.
What's special about TRIM is that this radar can measure storms from the Earth's surface up to the top of the troposphere and into the stratosphere.
The ultra-precise radar aboard the TRIM satellite emits a minute amount of energy, but it's capable of seeing the weather 250 miles below.
The radar sends its energy down in a tiny range, around 13 gigahertz, and in 1/1,000,000th of a second pulses.
But these minute energy signals are incredibly powerful scientifically. The TRIM satellite radar reveals exactly what is to be found inside the hurricane system.
The eye of a hurricane, normally you think of it as a very peaceful place. There's gradually settling winds, there's not any clouds, but the air at the bottom of the eye has been trapped there for a long time, and it's very moist, and it has a lot of energy, and occasionally it can break out of the eye into the eye wall and become the most energetic air parcels in there and ignite hot towers.
What this remarkable satellite revealed was that inside the hurricane there are areas of extremely intense updraft, super storm cells.
A hot tower is simply a storm cell that has a strong enough updraft that it's punched through the top of the atmosphere that normally contains weather, which is called the troposphere.
These dynamic storm cells explode upwards over 9 miles from the Earth's surface and into the stratosphere, so high that the temperatures are minus 112 degrees. Yet the energy of these so-called hot towers is immense.
Now, a hot tower by itself doesn't release enough energy to affect the fate of a hurricane. Put enough of them together, and you could. And so we know from these satellite observations that you can have a sequence of hot towers, one after another, sometimes just on one side of the eye. There can be a favorable region. So you'll have these mesovortices traveling around the eye wall, and when they hit the favorable region, a hot tower shoots up inside that vortex.
This convective burst on the eye wall of a rapidly intensifying hurricane is stupendously powerful. In 12 hours, it releases as much energy as the entire U.S. generates in over 2 weeks. This hurricane turbo-powered heat engine was only visible because of TRIM's unique radar view.
I feel as if it's peering into their personality, because you can't tell much from a person by looking at their face. If you have a sense of their emotions, and you get a better sense of who they are. So by seeing deep into the heart of a hurricane with TRIM, seeing every layer of it in three-dimensional detail, we get a sense of, is this storm really intensifying, or is it faking it? Does it just look like a storm about to become a monster storm?
Despite Owen's conviction that hot towers are fundamental to storm intensity, he believes the science is too complex for one simple catch-all answer.
There's controversy in what causes rapid intensification, and the answer is likely that it's not the same thing in every case.
With scientists struggling to identify the cause of rapid intensification, how reliable are the predictive models that depend on their observations? At the Hurricane Research Division, they may be on the cusp of an information technology breakthrough.
As computational power increases, we will be able to run hurricane models at higher and higher resolution. For example, right now, the large-scale fields, the large-scale environment of a hurricane model is executed at a resolution 27 kilometers. As computers becomes faster, more powerful, we'll be able to resolve this large-scale environment at even higher resolutions, such as 9 kilometers and 3 kilometers, as we currently do in the hurricane region.
As far as the numerical models, we are still a long ways away from getting to the point where we can trust numerical models to give us accurate RI forecasts. The tools we have to do so are better observations, but ultimately, from a prediction standpoint, we need to use computer models to improve our ability to say where these systems are going to go and how strong they will be.
Even so, in the uncertain world of hurricane prediction, there are some clear truths about the reliability of intensity forecasts.
You know, I don't want to sound like I'm bashing the models here, because you can't expect miracles. We really need to do a better job, in my opinion, of observing what goes on in the core of the hurricane and getting that into high resolution computer models. There's still a lot of work to be done, and that's not going to happen anytime soon.
What remains without question is that hurricanes are incredibly complex and powerful weather systems that we still struggle to fully understand, despite our commitment to science and funding. Brilliant scientists worldwide are initiating new research to try to increase the ability to predict hurricanes and get the message across.
But I think we need to look at these fundamental equations that we've used for decades and never thought to evaluate exactly in this way. Now, this is research that has not yet finished peer review, so this is what I'm currently working on.
With the causes of rapid intensification still eluding the scientific minds that struggle to unlock the puzzle, societies throughout the tropics remain at risk from cyclonic storms. It is clear hurricanes are a danger that cannot be fully predicted. And if it can't be predicted, how can the public ignore the potential dangers? Yet many people gamble by ignoring official evacuation orders and sit out hurricanes at home, which questions how fully we understand the risks involved. For hurricanes remain capable of inflicting enormous loss to property and life. The fact that some of the cleverest minds in science fail to completely understand and predict rapid intensity change renders the storms more deadly still. The percentages may be against a sudden major intensity change, but hurricanes thrive on being unpredictable. One has to ask the question, is it wise to tempt fate with the greatest storm on Earth? Every year, the tropical summer brings fear of hurricanes to the Caribbean and eastern United States. They are the greatest storms on Earth. Even the weakest inflict destruction. How can the living survive such storms? Because over the millennia, hurricanes have shaped the biodiversity of the Caribbean itself. The adaptations of life to hurricanes fascinate scientists throughout the Caribbean.
Hurricanes are hard for crocodiles, but no one really knows what happens to them in the swampland.
Hurricanes are part of what make Caribbean islands and rainforests what they are.
It's really hard to say whether a hurricane is a totally bad thing.
Because for better or worse, the wilderness is shaped by the extreme impact of hurricanes. The tracks of the hurricanes of the last 100 years reveal the full story of their frequency and reach. It is simply a quirk of fate that determines the size, power, and placing of each storm's impact. Every year, somewhere in the Caribbean, hurricanes will put the living to the test. Nowhere is tested more often than Cuba, home to a rare survivor from the age of dinosaurs. Here in the remote Zapata swamps are found the last representatives of a reptile that evolved over 135 million years, the Cuban crocodile. Hurricanes are now more of a threat than at any time in their long existence.
The program for the conservation of the Cuban crocodile began in 1959, right after the triumph of the revolution. At the time, the crocodile in Zapata was pretty much extinct. In 1979 was the first time that I visited the Zapata swamp, and unfortunately, it was also the moment chosen by Hurricane Frederick to pass directly over the Zapata swamp too. We had already spent 5 days working, marking several crocs when the cyclone arrived in the swamp. The hurricane brought really a lot of rain. The water level was terribly high and we were surrounded by crocodiles. It took us 4 days to get out of there. It was a big adventure.
Toby Ramos is the world's leading expert on the Cuban crocodile, now so rare that its very existence is doubted by many scientists.
We're going to go to last year's nest over there to see if it has eggs.
With the Cuban crocodile endangered, the health of nesting sites is vitally important. Nests are checked as part of Toby's conservation program. First, a little negotiation is needed with the guarding mother. The Cuban crocodile's main weakness to hurricanes are their eggs.
The biggest problem with the hurricanes is the raised water levels and the destruction of the vegetation. If that occurs during the reproductive season, the nest gets flooded. The chamber where the eggs are incubated fills with water so that it is impossible to get the gaseous exchange through the eggshell, and there is a high mortality rate. Here, our experience is that if a nest is flooded for more than an hour, the development stops, and there is no gaseous exchange. There is a lack of oxygen, so due to this, the embryo dies.
This nest is still in good health. With the mother keen to return, there's little time for the scientists to check her precious eggs.
The Zapata swamps are the last natural refuge where the Cuban crocodile lives in a wild state. There is shelter to protect them from the torment of hurricanes and winter storm winds. Here in the Zapata swamp, there is a hurricane roughly every 50 years. But during the last 20 or 30 years, we have had one every 4 years.
The increased frequency of hurricane flooding threatens the Cuban crocodile's ability to breed and repopulate the swamps. But this mother's long vigil is successfully nearing its end. Cuban crocodiles have a life expectancy of over 100 years. Time enough for some of these babies to face as many as 25 hurricanes in their lifetime. Practicing newfound aquatic techniques is vital training for these pocket-sized predators, if they are to survive both human hunters and hurricanes. To help ensure their future, Toby has been breeding Cuban crocodiles for 30 years, releasing them to repopulate the wilds of the Zapata. When they reach adulthood, hurricanes should be little threat, as long as they have secure aquatic refuge deep in the swamp. But the swamps themselves may be vulnerable. Nearly 200 miles to the north lies the Everglades of Florida, a vast wetland of unique plants that have been hit by several major hurricanes in recent years. At over 1.5 million acres, the Everglades are, in effect, an immense river, with billions of gallons of water moving southwards at only 2 inches every hour. Fueled by warm water, hurricanes lose little or no power as they cross the swamp. The first impact is felt by the mangrove forests, tough trees that grow in salt water and protect the coast for hundreds of miles. Thomas Smith of the U.S. Geological Survey studies the impact of hurricanes on this special wetland.
The mangrove ecosystem in Everglades National Park is critical to a number of species, many of which the normal park visitor doesn't see. An abundance of animal life, wading birds, small passerines, fish galore.
To fully appreciate the importance of the mangroves, you need to go underwater. It is an invaluable nursery and sanctuary for countless marine species.
If the mangroves disappeared, we would lose a whole variety of species. And there is a whole food web based on the decomposition of those mangrove leaves, starting with the bacteria, then going to little marine isopods and copepods, to the small fish that eat those, the wading birds that eat the fish. All of that would be severely, severely impacted.
And just what impact does a hurricane have on the mangrove fortress?
Hurricanes can actually do good things for mangrove forests, and they can do very bad things for mangrove forests. A small storm that comes through and has a smaller storm surge that brings sediment into the forest, you get a thin layer of sediment that comes in that can actually give you a little bit of protection from sea level rise.
But in the hurricane belt, a calamity always threatens. It is simply a question of time.
Hurricane Andrew was a definite turning point for people in South Florida. And I will never forget going through a neighborhood and not recognizing anything, because houses were gone, roofs were gone, vegetation was stripped. Hurricane Andrew did tremendous mortality to the trees. The sediment, the soil that the trees grow in is very soft. And so when a tree starts to sway, it's very easy for it to get blown completely over or snapped in half. So we had areas where there was, 50, 60, 80% of the trees were killed outright. Some of those areas have come back, some have not come back. It takes a long time for a mangrove tree to grow. Nature doesn't heal itself overnight.
Storms that reshape entire forests would devastate the urban jungle. Living in these seemingly benign residential areas can be risky, even to birds. Migratory purple martins heighten that risk by choosing to breed here close to hurricane season. In this community of Fort Myers in South Florida, local retirees help research into the birds' travel habits. But first, they have to catch one. For this task, you need more than a little time on your hands. The purple martin's choice of nesting accommodation makes them easier to trap.
Actually, never taken one out.
Ooh, nice.
The nesting of hundreds of thousands of purple martins depends almost entirely on human hospitality, but only for part of the year. Soon the martins will be starting their long journey south, and the veterinarian team hastens to get the tags in place.
We have a program that we are trying to track the purple martin to his home back in Brazil. And we are hoping that we can get some of these birds and put a geo-tracker on their backs.
The aim of the tracking program is to understand the physiological challenges of such long journeys on a fragile 2-ounce bird like this.
All good?
Oh, pretty good.
William?
They also take blood samples, and they also put a band on them so they'll know where those birds came from if they should light at another location.
Their life cycle forces them to navigate south across the Caribbean to South America in the peak of hurricane season. Careful veterinary records will help reveal how they endure such travels.
They'll start migrating from Canada in August and pass through here in late August and early September.
It's real good.
Of key interest is whether GPS data shows the purple martin to actively avoid storms by the timing or rerouting of their flight plan.
Are you ready?
Flight affords birds a quick escape route. Yet the Caribbean flamingo is at risk. They live in colonies scattered around the Caribbean Sea, but breed at only 4 principal sites during hurricane season. All the breeding sites are vulnerable to storm landfalls, including at some 100,000 birds, the most important. Rio Maximo in the north of Cuba. Jose Leal is the head of a network of specialists studying the flamingo in the Caribbean. His research site is the Rio Maximo wetlands, where he sees a tangible benefit from hurricanes.
Hurricanes have such a strong effect that we have to see it as a positive that can actually help the redistribution of species. When a hurricane hits elsewhere in the Caribbean, flamingos migrate here to take shelter.
As birds fly in, escaping from hurricanes elsewhere in the Caribbean, the flamingo population at Rio Maximo changes significantly. In past storms, refugees have come from the population found at Rio Lagartos in the Yucatan Peninsula of Mexico. Here, too, observers are seeking to understand the effect of hurricanes on the distribution dynamics of flamingos. Alex Zib-Che is an authority in the Yucatan.
When a hurricane is approaching, any flamingos that can try to flee the area and abandon their feeding grounds, leaving for other feeding territories like Cuba, Florida, Texas, or even Venezuela. We know that there are refugee flamingos from the Yucatan trying to escape hurricanes because after the storms, we have reports of sightings and can identify them using the leg rings that we put on them, right here in Yucatan.
Newly ringed juvenile flamingos would be like skittles to a coming hurricane. A bowling ball scattering all in its path. In Cuba, as in every corner of the Caribbean, each new hurricane spreads flamingo populations further and further apart.
Now is not one population, but multiple populations, amongst which the gene pool is shared, and the flamingos have become a species that hurricanes move from one point to another.
The Caribbean flamingo is mainly found along the Caribbean, but there's a little population on the Galapagos Islands.
Almost certainly, this population was driven here by an immense hurricane from the Caribbean.
We suspect this because as late as 1836, Darwin did not describe any sightings of flamingos there.
The ability of flamingos to outfly hurricanes and colonize new territories means that these storms may actually help efforts to expand declining flamingo populations. But hurricanes can be unpredictable and deadly, variable in size, force, and timing. Sooner or later, one will coincide with a flamingo nesting event.
What would happen if a huge hurricane were to come here when the flamingos are in their nesting season? In that event, the flamingos would not flee their nests. How many flamingos would die out of the global population of these species? It would be a grave threat for a species that is already at risk. The most common tendency for riding out a hurricane is to go deep into the closed mangrove lagoons and huddle as a big compact group. We've observed them sheltering like that during a hurricane.
If the mangroves uproot, the hiding flamingos will die.
To safeguard against this fate, as many juveniles as possible are brought into Leal's sanctuary.
Once the hurricane is past, we let them go back to the wild. When there are more breeding places like this in Cuba, there are now 4 where there's breeding every year, and the more there are, the more the threat of hurricanes to this animal will decrease.
For a hurricane to be damaging or beneficial boils down to timing, whether the flamingos are breeding or are free to fly before the storm. The more isolated the land, the harder it is to escape from a major hurricane landfall. Several have hit the island of Puerto Rico. Finding shelter here is vitally important. These hills are riddled with caves, and at night they come alive.
Most species of bats in the continent don't use caves as their main roost. However, when you come to the West Indies, most species of bats, they roost in caves.
Armando Rodriguez Duran explores the unique underground ecology.
Living in a cave is an advantage because of the frequency of hurricanes passing through the islands. Caves are a safe place, and they will protect the bats from the wind, from the rain,
and from the effects of any hurricane.
Some of those caves can host populations in the hundreds of thousands. The largest we have ever estimated is over 500,000, but colonies of 100,000, 300,000 are not uncommon in the region. What limits the number of bats in the caves is actually the size of the opening. The cave itself inside has much more space than what the bats are using, but they all have to come out and feed at night. So there's a limit to how many of them can come out in time to actually go and find insects out there.
While Armando takes his measurements, more and more pour out to feed. The 13 types of bats dwelling in Puerto Rican caves fall into 2 categories. The first are the insect eaters, like these. Sharing a cave-dwelling lifestyle with the bats could prove a risky venture for these honeybees. These are fruit eaters, the second category, seeking to gorge on mangoes, fruit that can be in short supply after a hurricane.
So what we have observed is that insect-eating bats tend to increase in numbers after the hurricane. The fruit-eating bats, on the other hand, what they find when they come out is that many of the trees have been are devoid of fruits, of flowers, and many of the trees are not even theirs. When that happens, they will come out and there will be no food for all of them. And that's when they face difficult times, and you will have high mortality of some of these species due to starvation more than to the hurricane itself. Some of the fruit and nectar feeding bats were the most abundant species in the caves, and then their numbers dropped after the hurricanes. The proportion of insect-eating species went up. As the number of fruit-eating bats went down, the insect-eating bats became dominant. That remains so to this day. So it may have changed the makeup of the cave until the next hurricane.
El Yunque Forest of Puerto Rico, The tropical rainforest here forms the heart of the island, 28,000 acres that harbor countless lush plants and animals. What would happen if this delicate refuge were to receive a direct hit from a hurricane? Scientists have been investigating this hurricane-prone environment for more than 40 years, led by Ariel Lugo.
In 1989, this forest was affected by Hurricane Hugo, and it received the heaviest winds in that storm, killed 37% of the trees, and it has the highest effects that we measure anywhere. So this forest was basically destroyed to a casual observer. Came here for the first time, many of the employees actually, they cried because they thought that the forest was beyond repair. That's because we had this idea that tropical rainforests were very fragile forests. Well, after the hurricane, we observed that all the big branches in the canopy, all the leaves of the forest were quickly transported into the forest floor. And in fact, if you were sitting here 23 years ago, what you would see behind me would be great piles up of branches and leaves that were previously on the forest canopy. So the forest changed completely in its aspect, because from a closed canopy dark forest, it was converted to a very open forest with these gigantic piles of debris. Hurricane Hugo, in 4 hours, deposited on the forest floor the litter, the debris that normally falls in a year. The scientists are trying to explain what are the mechanisms by which the forest recirculates the material that is dumped on the forest floor by the hurricane, and that's what we call the canopy trimming experiment.
To imitate a hurricane on a tiny scale, we need a big chainsaw. It takes a full day to trim a single tree. Hurricanes can destroy entire forests in just a few hours.
The canopy trimming experiment was an effort by the scientists in Puerto Rico to understand what controls the decomposition of the debris piles that are formed after a hurricane. And in that experiment, basically what we did is that we cut the forest and dump on the forest floor the amount that we had observed after Hurricane Hugo, and then study how the organisms responsible for the decomposition, how quickly they operated, how quickly they decomposed the organic debris.
Normally, leaves and branches that age and fall to the forest floor are brown and poor in nitrogen. But a hurricane rips off fresh wood and lush green leaves packed with nitrogen. This fresh debris is a rich source of nutrients, fertilizer to the surviving trees, and resprouting undergrowth. Now newfound sunlight from the storm-opened canopy conjures a magical change.
We were in for a surprise because this forest regenerated so fast at rates that we never even imagined before the hurricane. The material was recycled naturally within 5 or 6 years, because that's what hurricanes do. Hurricanes transport a lot of debris to the forest floor where it has to be processed before the forest can return again. So in this forest is where we learn a lesson about the resiliency of tropical forests.
This vigorous forest and its trees have mastered a strong hurricane response, but not all its inhabitants appear so resilient. These torrents hide creatures vital to the health of the mountain streams. Tamara Hartzell-Scally has studied them for many years.
This is a much better spot. We'll put one here. So in the Luquillo Mountains, there are many protected headwater streams, which are important freshwater resources for all the communities and the cities around them. And one of the less known but important and charismatic fauna of these streams are decapods, shrimp. We got a lot.
Tamara's passion for these small invertebrates is easy to see. She has identified that each species has a clear-cut function, essential to keeping their river home clean.
A lot of streams are like this size and even smaller, and they can be sometimes completely covered by the canopy and branches of trees. But some shrimp filter the water of the streams.
They are a tireless workforce for water purification.
They consume, it is estimated, between 40 and 50% of the biomass that falls at any given time in a stream pool.
Without these fragile creatures, the streams and headwaters of Puerto Rico would be completely overwhelmed by organic debris after storms and hurricane events, and little clean water would flow downstream. But how do they manage to survive the sudden arrival of severe storms and hurricanes?
People are not aware of how quickly and how high the water can increase with just rainfall that is not even occurring locally, but that may be occurring further up the mountain. Because shrimp are adapted to living in fast-flowing freshwater conditions, they immediately can take cues and change their behavior when you have an increase in flow or you have a change in the turbidity of the water. The shrimp that are usually inhabiting the deeper pools will probably be the ones that stay and hide under boulders. Of course, some are usually carried by the current, but they can step out of the current at some point and leave out.
Shrimp simply avoid the worst impact of the storm floods by walking on land.
And as long as they're wet and they're close to the water, they can migrate and move between pools and escape the current that can carry them away. There's not that much mortality in these events from shrimps just being randomly carried with the water current. The hurricanes give the shrimp the opportunity to recolonize the headwater streams. So in that sense, it's a restarting.
Hurricanes simply provide vast amounts of food for shrimp, the unseen guardians who keep the rivers of Puerto Rico running free. Hurricanes are a great threat to the city of Havana, Cuba. It is home to a world expert coral biologist, Pedro Alcalado, who fears the reefs are equally at risk as the ancient city he lives in.
The marine plate of Cuba is nearly completely surrounded by coral reefs. Out of over 2,000 miles of reef, almost 500 miles are shallow barrier reefs. In Cuba, they are in various states of deterioration. Only 6% of these coral reefs are still in a perfect state of health. The rest is generally quite damaged.
With Cuban reefs in decline, Alcalado leads an expedition to a site that holds a key to understanding the problems. The chosen reef is special because of its protective geographical location in the Cienega, which shelters it from most hurricane hits.
There are two reasons why this reef is the best conserved in Cuba and the Caribbean. The first is that its geographical position protects it with regards to the winds. The result is that when there is a passing hurricane, the coral suffers less in comparison to other reefs. There are also nutrients washing out of the soil in the swampland of Zapata, which enrich the water in plankton production that in turn feeds the corals.
A coral reef has naturally evolved to cope with hurricane damage. Branching coral like staghorn are adapted to regrow from any fragments broken off in storms. And on this reef, they're able to do just that. Here on this sheltered reef, even the critically endangered elkhorn is flourishing. On the way back, they stop at a spot that is fully exposed to the worst of the weather. This reef has been heavily damaged by several hurricanes. It shows no sign of any recovery. This is a cemetery.
After the passage of a hurricane, and because of the destruction of the coral, a lot of algae colonizes, as well as other encrusting organisms. This colonization prevents the settling of new coral larvae, which would otherwise have replaced those that have been destroyed. The slowest to recover are the corals and the fish. Of these, the coral are by far the most important because they are the ones that build the structure of the coral reef itself. They are the building stones. If a hurricane comes through every 6 years, this could be a good thing for the reefs. It helps increase the vitality of the coral by fragmenting the branches which fall on the seabed and sprout new growth, propagating and expanding the reef. But on the other hand, if hurricanes hit every year or so, there is no time for the reef to heal, and it slowly levels out, transforming into a debris pile. People often ask themselves if coral are going to adapt to survive hurricanes, and that's not really the right question, because the coral have evolved so that they've thrived during thousands of years of hurricane impacts.
Caribbean reefs should be capable of recovering from hurricanes, but the coral is now so weakened and diseased that once broken, it is incapable of normal regrowth. The reefs have been severely affected by human activities, with sedimentation, pollution, overfishing, global warming, and industry all taking their toll. Every year, the Caribbean islands lie in wait, waiting for the hurricane that sooner or later will surely come. When it does, instincts developed over millions of years will be essential for survival. On the island of Banco Chinchorro, east of Yucatan, 3 major storms have hit in the last decade. Even so, it is still the ideal research home for scientist Pierre Charrouot.
La Reserva de Banco Chinchorro is a very special place due to its unusual features. It's a site that is very isolated from the mainland, and it's a reserve, a protected site. These features mean that you can find significant wildlife diversity here. There is also a well-protected population of American crocodiles, which is unaffected by the intense hunting of the last century. It's a good population to study ecologically.
Pierre spends his nights here, checking for signs of his population of American crocodiles. All the more important because the island was submerged 10 feet beneath the sea during a recent hurricane. This caused a dramatic temperature drop that had a profound impact on the American crocodiles.
This sudden drop in temperature kills the embryos almost immediately, and they can survive below 28 or 26 degrees Celsius.
The American crocodile is adapted for life in salt water. Its eggs can cope with submersion, but they can't deal with sudden cold.
On precisely that night, we found a crocodile's nest. And in this nest, we didn't see a single baby born from that nest. You can see on this egg little marks, and these dark rings reveal that the embryo died right at the beginning of the incubation period.
On the island of Chinchorro, the respite for the crocodiles is short-lived. Tropical weather threatens the archipelago once more. During a recent hurricane, the winds drove a gradual 12-foot sea level rise over the island. with shelter fast submerging, even the adult crocodiles were forced to leave, to seek safe haven.
On immigration journeys, only the biggest individuals can survive at sea for a long time. Individuals over 13 feet long use the currents and can swim for hundreds of miles at sea without a problem.
Running on the seabed, they can work their way along seafloor shelves with minimal effort. Following the currents north, they head towards the Gulf of Mexico. Driven on by hurricanes, the American crocodiles have voyaged successfully at sea, enabling the species to spread and repopulate a wide geographical range that includes Cuba. The success of the arriving American crocodiles comes at the expense of their Cuban cousins. The bigger Americans have interbred with the Cuban species, which could become extinct as a result. There is one final refuge for the Cuban crocodile, from both invaders and hurricanes.
The advantage for Cuban crocodiles living here in the Zapata swamp is that there are cenotes. These are limestone holes filled with water, and when storm events happen, the crocodiles can shelter inside the cenotes without any problem.
But nothing is certain in the Caribbean, where hurricanes are a force of change, a destructive power that forces life to adapt, to mix, to restart. Hurricanes can be lethal at the level of the individual, but planet Earth functions at the level of populations and systems over long periods of time. Change is simply the force of renewal. Even a crocodile has no guarantee of species survival. Hurricanes are agents of destruction and of rejuvenation in equal measure. In the future, they may be more powerful and inflict greater change than even those of today. Can we adjust to match? The world's climate is changing. The sea level is rising. The ocean is warming. More heat to fuel the hurricanes that put us in harm's way.
The hurricane is the greatest storm on Earth, and it's capable of doing tremendous damage and causing large loss of life.
Is it possible that losses inflicted by the weather of the future may be even greater than those of today.
The changes that we're having on the planet as a whole could be affecting the frequency, the severity of these hurricanes, and I think that's something to be extremely concerned about in the future.
To prepare for our weather fate, science searches the past for clues to the long-term trends in storm events.
So by studying the past, we hope that it can help us better understand the present and to better predict the future.
With the planet's evolving weather, how well prepared are we to survive the hurricanes of the 22nd century? Over the ocean, a new storm gathers strength, churning towards land. In what weather world would such systems move 100 years from now? Predictions of future climate have won climatologist Jean-Pascal van Iberzel a Nobel Prize for Science.
Well, climate is going to change in the next 100 years, mostly through the effect of human activities and greenhouse gases. And the main change is an average warming of the temperature at the surface of the planet. And there'll be changes in the Atlantic storm activity.
Just how those storms do change concerns scientists and forecasters of the hurricane research community in Miami, Florida.
There is still significant debate about how hurricanes may change as climate changes.
There are modelers who are running 100-year scenarios that clearly show that the potential energy available for hurricanes will become greater.
Most of these climate models are saying that we'll have fewer numbers of storms and hurricanes as the climate warms. But then people also say that hurricanes are becoming stronger.
The strength of the landfall of Hurricane Sandy made it the second most expensive hurricane of all time. During the night of October 28, 2012, it would change the lives of thousands.
This is part of the Brick Township's 3.5 miles of the Barrier Island, and this is the aftermath of Superstorm or Hurricane Sandy. That house that you see behind us here was actually up by the beach, and that came down. So there's a truck underneath this house, obviously the forklifts that you see, and just the force of the water is really unimaginable, because when you look around and you see the devastation, never before I've lived here all my life, would I believe that I'd see something like this.
Despite its great size, this was a modest Category 1 storm, a deadly storm. But was it the superstorm of the future?
We were here for Irene last year, and the water came up to the edge of the boardwalk, never went any further, and it really didn't do any damage. There's been people that have been down here a lot longer than myself. They said they, in all their years, 50 years, have never seen anything like this, and you can see what it did. It had to be something, again, that no one could have ever expected to do this kind of damage.
If the storm only had relatively weak winds, why was it so destructive?
Sandy was producing Category 1 hurricane force winds, but it was such a large storm. Its area of tropical storm force winds extended from the Carolinas up through much of New England. When we're talking about storm size and storm surge, it's very important to think about how the storm is pushing this water on shore. If you take your hand across a swimming pool and push just a little bit of water, it doesn't move very much. But if you take your entire arm across the top of that swimming pool, you'll push a large amount of water. And that's what we're looking at with storm size.
So it is not simply how often future storms would strike, but how damaging they will be in terms of size and power. Satellites encircling the planet collect the best data for computer models of future hurricane trends.
Do we have more tropical storms and hurricanes in the historical database now than we did years ago? Absolutely, yes. And the reason for that, in my opinion, the primary reason for that is improvements in observations. I mean, if you think about it, before we had satellites, how did we even know we had a hurricane out in the middle of the Atlantic Ocean?
Satellite measurements were not available before with a good quality, and therefore we only have a relatively short record to talk about the trends in hurricane activity.
Official weather records only go back about 160 years. To extend our data set of when and where hurricanes have hit, we need to look deeper into the past.
Okay, that's about it. The last 160 years is too short for us to understand the frequencies of very intense but very rare hurricanes, and that is why we try to extend that record, that period of observation, from 160 years to 2,000 or 3,000 years, so that we can have a longer period of time during which more hurricanes like Katrina did happen. Okay.
But the past does not give up its secrets easily.
And so part of the objectives of our work here is to try to find evidence of ancient hurricanes and try to reconstruct their frequencies during the last hundreds or thousands of years.
The team are looking for traces of sand layers in the muddy swamp deposits, telltale signs of a powerful hurricane in the past. The soil itself serving as a natural archive of thousands of years of weather events.
Well, when we open our core, we expect that the storm surge deposit will have a different character visually, because the mineral and chemical composition may be different, and also the storm surge deposit may be of a different texture. Now you see this root here that's lying horizontally. It could have been washed in by water, but just looking at the color, you see it's very different. This is most likely the Hurricane Isaac deposit, and it may go from here down to about here. But when we come down to here, then we can see the silt and clay laminations, beautiful layers of, darker bands and lighter bands. This material might be several thousand years old.
By analyzing many cores sampled across an area, they'll be able to find out how often big storms have occurred.
We found that the most intense hurricanes, like Category 4 and 5 hurricanes, they have a typical rate of hitting the same site maybe once every 300 years or so.
The study of cycles of hurricane activity over time is helping geologists and climatologists to form a view of future climate trends.
Assembling all that information gives a relatively complete picture of how climate has evolved in the past. And that's very useful to validate the climate models in order to have confidence in them when they are used to look at the future.
Complex computer models lead them to believe that hurricanes may actually become less frequent, but that it is not the full picture.
In a warmer climate, hurricanes might become more intense, even though they would become less frequent.
Which means that although there will be fewer storms overall, more of them will be the most damaging of major hurricanes.
A hurricane is still a rare event, and our memories are very short. I've seen a lot of hurricanes, even here in Miami. We went through a Category 5 hurricane, Hurricane Andrew in 1992. But with time, people forget what these hurricanes can do.
Societies affected by hurricanes would do well to recall such major storms because the past can help us prepare for future impacts. One country that has not forgotten the deadly effects of hurricanes is Cuba. Jose Rubiera, head of the Meteorological Service, remembers a turning point in his country's storm planning.
Hurricane Flora was the first hurricane hitting Cuba after the revolution. It was in 1963. It was the second greatest natural catastrophe in Cuban history. Fidel Castro was very, very affected by the amount of casualties that Cuba had in this hurricane. It was a terrible hurricane.
As Cuba counted the cost, Castro's response was to create a new Institute of Meteorology with special focus on hurricane forecasting. Cuban society is structured in such a way that the lessons of Hurricane Flora are adhered to. Evacuation orders are obeyed, construction tightly regulated, and forecasting driven by a single clear voice.
Efectivamente, seguimos con más. La tormenta tropical Isaac continúa su paso por el Caribe insular. Y a esta hora nos vamos a comunicar con el doctor José Rubiera, el director del Centro de Pronósticos del Instituto de Meteorología de Cuba.
Bueno, aquí tenemos la
Rubiera's weather bulletins are the focal point for a state-driven hurricane action plan that is totally supported by the populace.
La fuerza de sus vientos hasta 100 kilómetros por hora. La presión en el centro ha bajado a 992 hectopascal o milibares. Eso quiere decir que es...
Nuestro pueblo ha logrado una cultura respecto a esto.
Our country, Cuba, has a long-standing understanding of hurricanes, mainly due to Dr. Rubiera's efforts. When a hurricane is close to making landfall, people are already evacuated. Cuba is one of the safest places to be when a hurricane event makes landfall. The Cuban authorities are very concerned about what will happen to the people.
The aim is state-governed protection, whatever the future brings.
In the last 17 years, we have seen 9 hurricanes stronger than Flora, and the loss of life have minimum.
But the storm-scarred buildings of ancient Havana serve as a constant reminder that direct impacts from future hurricanes have the potential to be catastrophic. Cubans are acutely aware that the worst may yet be to come. With global temperatures continuing to rise at 0.4 degrees Fahrenheit per decade, conditions are likely to foster the formation of increasingly severe storms. But even without the effects of climate change, the probability is that we will witness an Atlantic landfall from a storm of Sandy's great size and with the power of an Andrew or Flora. Such storms may become a more common occurrence, with up to a 50% increase in major category storms a possibility. The heavily developed coast of the eastern United States is at risk, nowhere more so than the thin strip of coastal barrier islands. Barrier Islands fringe thousands of miles of the East Coast, bearing the brunt of any storm weather and sheltering the mainland. Born and raised on Florida's East Coast, Tim Palmer is concerned by the changes he's seen in the local islands.
There's always been development on the barrier islands, but it seems like there's more and more and more development. Places that were all sea grapes and mangroves and casuarinas now a lot of times are host to condominiums and parking lots. You know, it's one thing to build on the riverside of the barrier island because that's going to be protected by the rest of the land, but when you start putting these high-rise condominiums on the ocean side, not only are you building them in a place where they could possibly be endangered someday, but also you're taking away that vegetation which gives the barrier island its fabric that holds it together. If you get a minimal hurricane, even that's enough a lot of times to punch through places in the barrier island. It's much more likely to do it once the sea oats and the sea grapes and the mangroves have been removed.
It's a problem that has been studied by a U.S. Geological Survey team led by Abby Salinger.
In a completely natural situation, the barrier islands would migrate landward, and they would have room to migrate landward. But around the country, we have built so much infrastructure in place, either on the barrier islands or just immediately on the mainland side of the barrier islands, that in a lot of places there's no room for the island to evolve further. You know, particularly places like Miami Beach or Ocean City or Virginia Beach with huge buildings. You have fixed the location in place, but yet the natural system wants to move landward. And humans now come in and try to maintain the islands where they are. And we have seen over and over that can be a losing game.
In 2011, Hurricane Irene crossed the Pamlico Sound in North Carolina as a large Category 1 storm. It attacked the Outer Bank Islands near Cape Hatteras, driving a storm surge of about 6 feet across the Sound. It breached the barrier islands repeatedly, the storm smashing bridges, shattering roads, and destroying houses along a 250-mile stretch of coast. Abby's team have surveyed the entire seaboard of the eastern United States using laser imagery called LIDAR, precisely mapping the topography to identify future weak spots in coastal defenses.
This is airborne LIDAR data, the first that we received back from our partners at NOAA. It shows very clearly the houses along the beach and how close some of the cottages here are to the ocean.
The islands themselves are extremely vulnerable to damage, and Tim believes construction only serves to increase that risk.
Every time we've had it break through, it always seems to be fairly near where we've changed things. Either we've dug a canal or we've built buildings. These barrier islands are pretty much made to shift around. They get bigger, they get smaller. The sand piles up, the sand washes away. When we put a building on it, that really kind of disrupts the natural cycle.
But desire to build on the ocean's doorstep is increasing. With sea levels rising, that puts more people at greater risk. The occurrence of major category storms is predicted to be more frequent, and with beach sand playing a vital role in protecting coasts, the scale of ongoing beach erosion concerns Alfredo Torruella.
When a storm impacts a beach, the beach sheds its sand, creating a sandbar which causes the waves to break offshore, taking the pressure off the beach. So it's sort of a self-defense mechanism, but that's a short-term phenomena which, after a storm passes, the normal waves then restore the beach to its previous condition. So that assumes a cycle.
But that natural cycle is already broken by coastal development. To compensate, the U.S. Army Corps of Engineers oversees a vast program of beach replenishment at the cost of many millions of dollars each year. In Florida, one of the world's largest dredging ships pumps marine sand ashore in an operation overseen by program manager Jackie Kaiser.
In Florida, the sand generally flows from north to south, and as development has taken place, we've hardened our shoreline, we've reduced the width of beaches, we've taken away dunes so folks can have an ocean view, which all intercept sand that would otherwise be moving down the coast.
Interrupting that natural southward flow of sand with human structures creates turbulence that results in sand being lost to the ocean.
As the shoreline recedes, we've moved forward with beach renourishment to try to maintain a shoreline and maintain a good width of berm to act as a protective barrier for hurricanes or major storm events.
The Army Corps budgets millions of dollars a year, both to rebuild beaches and dredge clear storm damage.
When the sand washes away, what the answer has been over the last few decades is to just pump sand from, the bottom offshore and to just pile it up onto the beach. I've seen this go on now for probably 25 years, and it seems as fast as they put it onto the beach, it goes right back off again. The sad thing is not only does all the work and all the money towards building up the beach seem to be wasted, but also the sand piles up on the natural reefs that we have out here just off of the beach.
When a hurricane erodes a beach, many people sometimes feel like, well, that was a waste of money. We spent all that money to get our beach and now it's gone. But that's exactly what we designed the beach to do, to sacrifice itself for the upland structures and for human health and safety and our infrastructure.
The immense task of replacing the natural cycle with engineering efforts will increase as sea levels rise.
If we stop dredging for beach renourishment in Florida, there would be a devastating effect to the economy. Tourism alone is a $60 billion industry or income producer for the state of Florida, and it's a great federal tax producer as well. The hotels, the streets, the schools, the hospitals, the roads would basically be abandoned at some point due to storm damages.
In economic terms, we need to keep pumping sand. But the question is whether the sand alone can adequately defend against the worsening storms of the future. With the danger from landfalling hurricanes increasing, the growing coastal populations need ever more protection to the built infrastructure.
Well, protective action can be seen in two categories. One is adaptation, is kind of weatherproofing, having better building codes so that when intense wind or rain comes, those infrastructures can resist better.
In 1992, Cat 5 Hurricane Andrew smashed into Florida, south of Miami. An event that was to change the standards of an entire industry. Today, hurricane safety building codes are enforced by inspectors like Eugenio Santiago.
I think Andrew taught us a very, very valuable lesson. We need to make sure that things are built the right way, both from the design point of view and from the construction point of view.
And just what dangers are those changed regulations seeking to prevent?
Well, the worst damage is what we call the envelope. The envelope is what protects the perimeter of the building. It's either walls or glass. And if one of those two fails, then wind gets inside and just destroys the building. You blow in a balloon, and you blow it long enough, the balloon explodes. That's what happens to a house.
This damage was inflicted by a Category 1 storm. We are threatened by far worse.
Hurricane Andrew will be remembered for an extremely intense Category 5 hurricane, but it was not the big one. Andrew was a small hurricane, extremely small. If we had a more typical size hurricane or even a large hurricane like Sandy or Katrina and the strength of Andrew, the damage would have been much, much worse.
Civil engineers like Forest Masters plan for precisely that scenario.
We're trying to reduce the loss of life and property during extreme wind events. And in order to do that, we have to have a very clear picture of the wind and wind-driven rain environment. The work we're doing is filling in a critical gap. We're taking measurements in the building stock, amongst the buildings, in hurricanes. This is where the damage happens.
Those field observations are taken to the laboratory to be tested in safety. But first, they have to recreate the hurricane.
So we built a machine to replicate hurricane conditions in a controlled setting. We can generate up to 230 mile-per-hour winds, and this creates significant pressures on the roof coverings. And in turn, that allows us to find exactly when the failure threshold is expected to occur. Let's bring it up. Where we can carefully control the wind speed to replicate what happens on an actual roof.
The end game is to design roofing materials that can withstand the wind speed of the most severe hurricanes. $28,000 houses were destroyed by Hurricane Andrew in less than 24 hours. In the most severe winds, even vertical structures are at risk. To test designs, the team built the dynamic pressure loading actuator, which creates hurricane load conditions on the side of buildings.
Daniel, put the camera on the second panel down from the top.
Okay, just make sure the traceable spheres are in the line of sight.
Okay.
Yeah, that looks good.
All right.
Okay. This particular system is designed to produce an extreme amount of pressure. Think about the types of loads that would occur on the top of a skyscraper in a Category 5 storm or an EF4 tornado on a low-rise building, and that would give you a sense of the magnitude of the power. Okay. All set?
All right, Scott, go ahead and start the engine so we can begin the test.
Okay. Ultimately, we're trying to create an environment where manufacturers can push boundaries, they can try new things, they can innovate, and understand that what they're seeing is actually what will happen in a real hurricane event. And that hopefully will give them the confidence they need to push forward to keep advancing their technologies.
Civil engineers are improving modern designs with the aim of surviving Category 5 wind speeds of 150 miles per hour or more. But a major storm landfall brings far more than just wind. It's a problem that focuses the attention of physical oceanographers at the University of Miami in Florida. A major Category 5 storm may have waves well over 30 feet high. And it's not just the wave size that matters, because their height can be doubled by the storm's tidal surge. Here, they can study in safety the potential impact of waves on man-made structures using models. With rising sea levels, the damage from future storms will be even greater.
Sea level rise is a parameter that is now well measured throughout the world. And it is now very clear from those measurements that sea level has increased on average by almost 20 centimeters since the beginning of the 20th century. And it's only the beginning because the projections for the end of this century show a possible increase in sea level that's between 30 centimeter, 1 foot, and 1 meter, more than 3 feet. Potentially, big changes for millions of people living close to coast.
Whatever form the hurricanes of the future do take, there is no doubt their reach will stretch ever further inland. The changing pressures and extreme winds of a major hurricane may cause a tidal storm surge 20 feet high. As rising sea levels force such surges to new heights, coastal erosion is set to increase.
Beach erosion is driven by high energy events, really. And because Puerto Rico is in the smack dab in the middle of the path of hurricanes, every summer, or every hurricane season rather, we are subject to serious erosional events. So absolutely, hurricanes play a big role in beach erosion in Puerto Rico.
And that role is likely to grow if major hurricanes become more common in the future. But San Juan has an unlikely defense.
The reefs off San Juan are actually surprisingly healthy in certain pockets. Of course, there are areas that are quite devastated, but it's amazing to be snorkeling and looking at some beautiful corals and stick your head out of water and see a metropolitan city just 1 mile away.
Alfredo has known for years that reefs absorb wave energy, but he didn't know by how much. In 2011, he had a chance to find out.
Tropical Storm Irene is just east of Puerto Rico, and we're hoping that it intensifies to a hurricane anytime now. Well, the idea is to record the currents and waves during the storm, something which has never actually been done here in Puerto Rico. But ultimately, we want to see what effect the waves have on the erosion of the beach as they are transformed by the effect of the reefs. Because there's a protective reef offshore in front of the city of San Juan, and we want to see how they interact, how the reefs interact with the waves and the currents, and what effect that has on the erosion of the beaches during the storm.
With the storm a mere 18 hours away, there's no time to waste.
Essentially, the instrument is about a 3-foot cylinder, and we affix it to a base that's custom made, and we go diving and go to the bottom of the ocean and secure it to the bottom of the ocean. We placed these instruments outside of the fringing reef and inside of the fringing reef so that we could have a record of the waves and the currents associated with the storm, with Hurricane Irene. Later, we took that information and used it to calibrate a model of the entire area. And using the model, we could examine the wave patterns and the current patterns that the hurricane generated.
Irene strengthened into a Category 1 hurricane over Puerto Rico, with powerful waves striking the north coast. The 30-foot waves generated by Hurricane Irene as it passed San Juan lost over 90% of their energy on the offshore reefs. Only 10% reached the beaches of the city.
If those reefs weren't there, the impact on the shore, the energy arriving on the shore would be 10 times as great. If you want to understand the forces involved, picture this. 1 cubic yard of water is approximately 1 ton, similar to the weight of a small car. Well, imagine a wave containing dozens and dozens of cubic yards of water hurling at you about 20 miles an hour. The forces are certainly significant. Take that up to the next level. A hurricane generates waves in excess of 30, 40, 50 feet. We're talking literally thousands of the equivalent of small cars being hurled at you at 20 miles an hour. The impact is truly devastating. And now we have one more reason why we need to preserve these reefs, and that reason is that without the reefs, they would not block the wave energy during storms, and the city of San Juan would not exist as it does today.
Many cities around the Caribbean Sea were built using the protection of offshore reefs. But today, those reefs are in serious decline. The loss of protective coral reefs is a vital issue in low-lying South Florida, where the Mote Marine Tropical Laboratories research into solutions, led by David Vaughn.
The Florida Keys are a place where our elevations here are only a few meters. So without our barrier to wave action and storms such as a coral reef, it's critical here in the Florida Keys. We've lost a decent amount of our outer reef corals. Those were the first barrier to things like storm surges and wave actions. We have lost 25% of the world's corals in just the past 20 to 40 years because we've lost some of those bigger outer reef corals like the elkhorn, those majestic corals that were out in the forefront, but 98% of those are gone. And so now our coral reefs are much more susceptible to wave action.
In its natural state, coral is less and less capable of protecting shorelines from hurricanes. Its decline is largely a result of human activities, such as overfishing, industry, and pollution. But can the clock be turned back?
In any other species, they do what's called restoration. If a forest burns down, we know how to grow a new tree and replant a forest. We've been trying over the past 10 years to see if corals can be restored and replanted. And the good news is it's working. Not only working, it's working even better than I originally thought.
One team of biologists from Mote Marine is aiming to restore the reefs of the Caribbean.
Staghorn coral has always been adapted to deal with weather events like hurricanes. A big part of its natural process for reproduction is that it can break into smaller pieces during storms and events like that. And each of those pieces can anchor themselves to the reef and reestablish as a whole new colony.
But those staghorn colonies have all but disappeared.
It's one of the most important corals here in the Florida Keys as far as building the reefs. And it's also one of the ones that's in the greatest decline in the last few decades. It has the greatest potential, though, for restoration because it's one of the faster growing species of corals here in the Keys. But a bigger part of this project is we work with partners throughout all of South Florida and the rest of the Caribbean so that we have these coral nurseries spread out throughout the Caribbean, all sort of following the same procedures and with the same intent. But that way, no one nursery is, if we were to be impacted by a storm or hurricane here in the other Keys, we could just work with our other partners in other regions and the project would continue to move forward.
Yeah, great.
Flourishing in the shallows is a farm of living rock. Healthy, live, hard coral has a thin outer skin of living tissue that manufactures an inner limestone skeleton, which gives strength and form.
Because we live in an area that's prone to a lot of hurricane impacts, we've had to take that into account with the way that we grow our corals. We grow it in several different methods, anchored to the bottom. Some of them are hanging in mid-water structures that can move with the waves and the tides. These corals, they grow quickly, and if we do it in a controlled environment where we can take care of these smaller pieces and grow them up to a size where they're strong enough to deal with some of these other stressors out on the reef, and we put them out in the reef in enough numbers and with enough diversity, we're actually going to make these small, compact populations that will cross-fertilize each other and repopulate the entire reef tract.
But the ocean itself is changing, making the task ever more difficult.
We have burned a little more than 500 billion tons of carbon since the beginning of the industrial period. Around 150 billion tons of that carbon have been absorbed by the oceans, therefore contributing to the acidification of the oceans, which is also a problem.
Acids dissolve calcium carbonate, which forms coral skeletons. It is whether an acidifying ocean affects living coral that is the subject of research here in Miami for scientist Ian Enochs.
Corals are very complex structures. They have all sorts of surface indentations, multiple branches, and because of that, we actually use 3D scanning. Here I have a sample of the endangered staghorn coral. We have grown these corals in a laboratory that we have that very precisely mimics conditions that are predicted for the end of the century. So we can monitor living corals as it changes in different ocean acidification conditions.
By using scanning techniques to look inside the coral skeletons, they have confirmed that it is becoming weaker and less capable of growth.
So we know that ocean acidification affects reefs in really two different ways. One, the corals actually slow down, and two, the natural organisms that erode the reef, that actually increases as well. So we have a really difficult situation of slowing growth and increasing erosion. And clearly this is very difficult to maintain a healthy reef ecosystem.
If the ocean continues to acidify and warm, coral reefs will find it ever harder to grow in a sustainable fashion. The team at Mote Marine are trying to preempt the changes.
We're definitely trying to predict what the reefs will be like, whether we like it or not. I guess we are building a reef of tomorrow.
Identifying what exactly the coral of those futuristic reefs will be is the focus of new research.
The experiment we have going on is called our ocean acidification system, in which we can vary the pH from what it was a few years ago to what it is today to what it may be 20 or 50 years from now.
And in the offshore farm, there are plans for the future as well.
Our Staghorn project, by design, was trying to get as many genetic variations of the same species out there. And so we're watching all of these different coral genetic strains. Some seem to be growing better, and we'll see in the future with different ocean conditions which ones are going to be winners.
If global warming goes unchecked, the ocean will continue to become more hostile to coral growth.
So 50 to 100 years from now, we may have to restore corals a couple of times before there's no longer a threat by global warming, high temperatures, and ocean acidification. But I'd like to see the potential of, in 10 years, to almost completely restore the reefs the way they used to be.
Despite these efforts, with climate changing, coral faces an uncertain future. Just like the barrier islands, the natural defenses our forebears built their cities behind are becoming ever less secure. Events of November 2013 set a terrible precedent. When this monster storm made landfall, it completely destroyed the city of Tacloban in the Philippines. 45-foot waves and 200-mile-per-hour winds left at least 6,000 dead. It was Cat 5 super typhoon Haiyan. Scientists predict such superstorms will become more common worldwide. How seriously should we take these predictions?
We can't make a reliable intensity forecast out to 5 days, so I'm not sure how accurate that it's going to be out, 100 years.
Validating a climate model based on the data we have of the Earth's historical past is difficult.
we have very little relevant data available with which to make a comparison with our ongoing simulations.
What is clear is that the sea level increase will render the effects of hurricanes and tropical storms in general stronger and more damaging.
No matter how many hurricanes we have in the future, if there are more hurricanes or fewer hurricanes or the same number of hurricanes, whatever hurricanes we have are likely to cause more damage because of the gradual sea level rise.
And it's not a simple linear function. It's not like sea level went up a foot, therefore the tidal surge will be a foot higher. It's much more complicated than that. It could be many miles further inland.
Despite the increasing danger, the desire to build right on the ocean's threshold is continuing unabated. Wilderness, with its remaining natural defenses, ever more rare.
If you look at development, we continue to develop these coastal areas, these very vulnerable coastal areas. And most local politicians see that as a good thing. If you increase the population and have nicer homes, which we usually have on the coast, that increases the tax base.
But development in search of economic benefit risks putting society in harm's way, from which science alone may not be able to protect us.
The problem is much wider than just a scientific problem. It's also a technical problem, an economic problem, a human problem, a moral problem.
To solve these problems collectively, perhaps our crowded society of today should take note of the wisdom of citizens in Louisiana over 150 years ago.
In central Louisiana, there's an island called Ile de Nere. It's the last barrier island to the west along the coast of Louisiana. Back in the 1850s, it was developed as a resort. One year in 1856, a hurricane came along, and it killed half of the people there. Every house, every structure on the island was laid flat. And what happened was they decided not to rebuild. Within the United States, this is very unusual. After a major storm comes through, our first response is to go in and rebuild along the coastline, and commonly to rebuild bigger, more elaborately, very close to the beach.
Rather than rebuilding more and more grandly after each disaster, imagining that everything can be just the way it was, shouldn't we consider changing our habits?
Because if we only try to adjust to that warming climate, and if we do not work in the area of prevention by reducing greenhouse gas emissions, it will not be possible anymore to adjust for the increased intensity of those damages.
In an uncertain future, there are certainties. Natural habitats are weakening. Urban coastal developments are increasing. And sea levels are rising. As fast as we build, prepare, secure and maintain, trying to conserve and reshape the coastal strip, working ever harder to preserve our lifestyle, it seems the elemental Earth is changing faster still.
Good morning, Florida. It is 8 a.m., August 4th, 2109. Another Category 5 landfall is imminent in Miami. The second Cat 5 to hit the city in the last 6 years. Storm surge has flooded tens of miles inland. I-95 is driven